So today we're going to look at Newton's laws. So we're going to look at the first and second law today, and then we're going to look at the third law next class. So before we look at Newton's laws, there's a couple of background things that we need to cover. So the first thing that we need to cover is forces. What's the definition of a force? Because all of Newton's laws talk about forces, so what's a force? Well, a force is pretty simple. It's a push or a pull. Up there it lists different things that you should know about these forces. Again, the whole point is that it's a push or a pull that transmits energy. It's a vector, that means it has magnitude and direction. The third bullet point is of particular concern, and it says it exists when objects are interacting, stops when the interaction is over. That seems pretty obvious. But I want to highlight that particular bullet point because so often when students are doing problems, it'll be a problem like, oh, you throw a ball up into the air. As the ball is going up, and it stops and it starts to come back down. What forces are acting on this ball during its flight? Well, in that case, the only force acting on the ball is simply the force of gravity. Gravity pulling it down. However, I get a lot of students that will tell me, well, you also have the force from your hand on it. I'm like, what? Well, you threw it. Okay, yeah, you threw it earlier, but you're not still throwing it now that it's in the air. So the whole deal is, once you stop pushing it, that force does not exist anymore. It existed when you pushed on it, but as soon as you stop pushing, it doesn't exist anymore. That's what this third bullet point is trying to get at. So don't try and put forces in that aren't there. Once the two objects have stopped interacting, the force is gone. Okay? That's very important to note because later on, I'm going to have you identify forces that are acting on objects. And if you don't correctly identify them, if you think that you're still pushing a ball when you're not, well, that's going to lead to a bunch of wrong answers. So make sure you note that. Also on here, it gives you the symbol for force. We're just going to use the letter F. Now you should note that whenever we talk about forces, there's multiple forces that are possible, and those forces can all act on the same object. So what we do is we write the letter F for our force, but then we're also going to give it a subscript, that's a little letter at the bottom, to make sure that we label the force, that way we can tell one force apart from the other. And then it gives us our units. In this class, we use the metric system. So we have the unit of newtons for force, but note that that's what we call a derived unit. Force is actually calculated by multiplying mass and acceleration. Our unit for mass is kilograms. Our unit for acceleration is meters per second squared. So force is a mass times, or kilogram times a meter per second squared, which physicists are lazy, so we just call that whole thing in newtons. So you guys got to know that kilogram meter per second squared or newton is the same thing. All right. So are there any questions about that? All right. Here, this gives us two categories for forces. It says contact forces, long-range forces. It's pretty self-explanatory what those are, but there's really no need to categorize them. I mean, obviously some people do. So, contact forces, two objects are touching. Long-range forces, the objects don't have to touch. So, it gives you the example of gravity. Can y'all give me another force that acts over a distance? Kind of wind. I was thinking more about those pesky magnets. Y'all ever play with magnets? Yeah, like the poles, like they can push each other without actually touching. Okay, so like I said, those are different force categories. I wouldn't worry too much about them. I'm certainly not going to ask you questions on them. But this slide and the next slide list a few of the forces that we will talk about in this class. This is not a complete list. There's obviously forces that could occur that are not on this list. The main reason for this list is for two reasons. Number one, we talk about forces that we're going to see a lot, common forces, and then some forces that are a little bit misunderstood. So we want to make sure we have a good definition of those before we move on. So for instance, it starts with frictional force and gravitational force. Those are pretty common. Gravity is pretty much going to be in every problem, presuming you're here on the Earth. So the force of gravity pulls objects down. Pretty simple. However, what's not so simple about gravity is that it's also known as your weight. So your weight is the force of gravity, and you guys got to know that, because I will give you problems, and sometimes I will say the weight of the object is blank, or also the gravitational force on the object is blank. You guys have to know that's the same thing, okay? Because sometimes I'll give you a question and be like, the gravitational force of the object is blank. What is its weight? You have to know that's the same thing. But you should also know that the weight of the object is not the same as the acceleration, right? Whenever we talk about gravitational force, I'll say, okay, what's the force of gravity on this? The students will be like 10. No, that's the acceleration of gravity. Acceleration and force are different things. It's really easy to keep them separate because gravity pulls you all down at the same rate. It pulls everyone down at 10 meters per second squared on Earth. However, do all of you guys have the same weight? No, not at all. You guys don't have the same weight because you have different masses, all right? If force is mass times acceleration, and we're talking about Newton's second law, well, if the force is gravity and the acceleration is 10, well, if I take your weight in newtons and I divide by the acceleration of gravity of 10, then I'll get your mass in kilograms. Up at the top talks about frictional force. It's pretty easy. It's just any force that opposes motion. So again, if you roll a ball along the sidewalk, it'll eventually roll to a stop because of friction. And friction is going in the opposite direction of the ball's moving. Here at the bottom of the slide, we have spring force and the tension force. So spring force is pretty simple. It's the force in a spring, but it's a restoring force. So, if you compress the spring or stretch the spring, it obviously wants to go in the opposite direction. And then tension force is simply the force in a rope, chain, or cable. And note that tension forces can only be pulls that you can't push. Because honestly, if you try to push with a rope, it doesn't go anywhere. And then on this slide, we have a couple more forces. We have what we call the thrust force, the normal force, and the net force. The thrust force is just a general term that we can use for what's moving things, so like a car or a rocket or even a person. We can say, well, it's the force of thrust. It's the thing pushing it forward, right? Even though a person walking is a far cry from a rocket ship, in both cases, something is propelling them forward. Rather than getting down into the minutiae details of what's actually going on there, we can just say, hey, something's pushing it. We call that the force of thrust. Then we have the normal force. And the normal force says it's a contact force of the surface on an object, always acts perpendicularly to the surface. It's usually the same magnitude as the object's weight. We'll come back to the normal force because that one can be very tricky. And then the last one it lists up here is the net force. The net force can be kind of tricky if you don't understand what the term net means. The net means net, not like a casting of a net, but a net like in terms of net gross. Net means if you have a bunch of forces that are acting on the object, you can add them all up, and the net force is what you actually see happening to the object. Right? So whether you have 1 or 50 forces, they can all add up to give us just one net force. And we can use that to calculate what's actually occurring. In that case, the actual acceleration of the object. So if it gives you an acceleration of an object and you know its mass, well, you can just calculate the net force that way. Because in the end, you only have one object and it only has one actual acceleration. Now here's the deal. That net force can add up to any number. It can add up to 0, it can add up to anything. If it adds up to 0, there's a big misconception. Because you can be like, oh, well, they all add up to 0, so it must be 0. Well, not exactly. If the net force adds up to 0, What that means is the object has zero acceleration. It could be, like this bowling ball sitting here on the stool, it could be exactly zero. Not speeding up or slowing down. It's just not doing anything, it's just sitting right here. This has a net force of zero. However, it could be an object traveling with a constant velocity. Like you can think of a car traveling straight down a road. If it's not speeding up or slowing down, it has a constant velocity. So it would also have a net force of zero. Okay? So keep that in mind. But let's go ahead and talk a little bit more in depth about this normal force, because it's a little strange and it can lead to a lot of questions. So what I'm going to do here is I'm going to look at a scenario or two with you guys. And I want you guys to think about a couple of things. So later on in the notes, it's going to give us the definition of what's called a free body diagram, and we're going to work on making some. But I'm going to actually make a couple of free body diagrams right now to help us understand the normal force. So to start us off with, we're going to look at this bowling ball sitting on the stool. All right, so I have a stool here, right? A couple of rungs. And I put a bowling ball on it. Y'all see that? So if the bowling ball is just sitting on the stool, let's draw a free body diagram for it. So the free body diagram involves representing the object with a dot. So there's my bowling ball. And then we have to draw and label all of the forces that are acting on it. Now, in the case of the bowling ball, there's only a couple of forces, so this should be pretty easy. So first of all, can you, what is holding this bowling ball here on the stool? Do y'all see any forces acting on this bowling ball? If it's on Earth, what should be pulling on it? Gravity should definitely be pulling on it. What direction is gravity? Yeah, typically just straight down, right? And so I can label this as the force of gravity. Now, one of the nice things about a free body diagram is it should, even if you think, okay, that's the only force acting on it, well, go back and you look at this. Go, okay, I think only gravity is acting on this bowling ball. Okay. Well, if only gravity is acting on this bowling ball, then the object would do the net force of what you see here. Well, I've only got one force, so the net force would be equal to gravity in this case. So my question is the bowling ball going down? Is it accelerating downwards? No, it's just sitting here. So that should indicate to you guys that there's at least one more force that we have not identified. Does that make sense? So, what do y'all think? Yeah, there must be a force going upwards, right? Now, if I draw this force going up, remember these are vectors. So the direction matters, obviously the up or down, but also the size matters, okay? Now, in this case, what do y'all think is holding this bowling ball up? Well, the stool. So I could call this F sub S for force of stool, but I already have an F of S. But it's more than just that, because here's the deal. If I take this bowling ball and I put it on the table, this ends up with the exact same free body diagram. Does that make sense? Or if I take the bowling ball and put it on the floor, or even if I just hold the bowling ball in my hand, I will get the same free body diagram. It's always gravity pulling it down plus something holding it up. So I could say, the force of the stool is holding it up right now, or maybe force of the desk in a minute, or maybe force of the floor, or force of my hand. But in the end, it's always this force that's basically the same size as gravity, and we know it has to be the same size as gravity because is the bowling ball moving? No, it's not moving. It's not moving up, and it's not moving down, like into the stool. It's just sitting there. So both of these forces have to be the same size, okay? And because no matter where I set the bowling ball down, this has to be true. I'm not going to call it the force of the stool, the force of the table, the force of the floor. I mean, you could. But scientifically, it's better if we use something that's more specific than that. But we can use it in any situation. And we call this thing the normal force, right? So I'm going to call it F sub n for normal. And this is the normal force we just saw on the slide. And so in this case, you can see that the normal force is indeed equal to gravity, but in the opposite direction. Now, I want to give you another scenario. I'm using this eraser here. Do y'all see my eraser? I can also put this eraser on the stool. So if I put a little eraser here on the stool. Come on. I don't like it very much. There's my eraser on the stool. Now with the eraser sitting on the stool, if I said, hey, draw a free body diagram for the eraser now. Well, what forces are acting on that eraser? Gravity. So I'm going to have gravity again. Now let me ask you, should this force of gravity be the same size as the force of gravity on the bowling ball? Does the eraser and the bowling ball, y'all think they have the same mass? No. The acceleration will be the same, right? They're both 10, but they have different masses, so therefore they'll have different weights. So I'm going to draw this one smaller. Everybody okay with that? So I'm going to say eraser here. And then again, the normal force, and again, it should be just as big as the force of gravity, right? Now, here's the deal. I drew it smaller because, it should be smaller than the bowling ball. But if I had just drawn one, we wouldn't really have a scale for the other. I want you guys to realize these are basically the exact same free body diagram. Y'all with me? Can y'all agree? Does that make sense? Now I have a very tough question for you. If I was holding the bowling ball in my hand, let's say I hold the bowling ball in the left hand, and I hold the eraser in my right hand. This is essentially the situation that's occurring here, right? Now, if you were holding these, you could feel how hard you have to push up to hold the eraser and how hard you have to push up to hold the bowling ball. Which one requires more force, the bowling ball or the eraser? Bowling ball. Everybody okay with that? Now, when you're holding them, I think we can all agree, okay, if somebody asks you to hold these things, you realize, oh, one is heavier, so I have to push up harder, right? That makes sense. But I put them on the stool. How does the stool know to push harder on the bowling ball than the eraser? I mean, we agree it has to be pushing harder on the bowling ball, right? Because if it's not pushing the exact same as gravity, well, then the bowling ball is going to move up or down, or the eraser will move up or down. But neither one is moving, so therefore the stool must be doing exactly what you do when you hold something, right? Now, it makes sense when you hold it. Not exactly. But it does have something to do with the surface. And this is actually why it's called the normal force. Because I want you guys to realize that, I can put anything down on the stool or on the floor, the stool or the floor, it's not alive, so it doesn't know how hard to push. But no matter what I put there, it pushes with the exact right amount. So the question is, well, how does it, quote unquote, know? How does it know exactly how hard to push? Well, the answer is, you guys actually already know this answer. What is everything made out of? Atoms. And atoms are made out of electrons, protons, and neutrons. I know you're like, oh, okay. Bear with me. On the outside of all of those atoms are electrons, right? What do you know if I take one electron and bring another electron near? What do? Do they like to be near each other? Do they attract or do they repel? Two electrons. They repel, they're the same charge. But here's the deal, if you think about this bowling ball, in my example, the whole outside of the bowling ball is going to be covered in electrons. That's the outside of all of the atoms. Well, the stool, the outside of all of the atoms of the stool are going to be electrons as well. And so when you take a bowling ball and place it on the stool, you're forcing the atoms of the bowling ball to get closer to the atoms of the stool. And by atoms, specifically I'm talking about the outside, which is just the electrons. And when you push electrons near other electrons, they don't want to be near each other. But the closer you push them together, the more they push back. And so something like the bowling ball, which is heavier than the eraser, gets pulled down by gravity harder because it has more mass. And therefore, the electrons will push back harder because they're closer together. That's how the stool or the floor or anything knows how hard to push, because of how hard you're shoving something into it. It's literally the electrons repelling each other. And on a deeper thought, if you realize that that's what everything's made out of, well, your hand's made out of atoms. Can electrons touch other electrons? No. So can you actually touch anything?
Is that like the thing where you're saying how it gets like really close on a subatomic level, but you don't have to connect?
Yes. So that's just a weird thing to think about. I'll let y'all stew with that one. But hopefully this makes a little bit of sense of, first of all, why we call it the normal force instead of just like a force from the table. Because this happens with everything. The normal force is indeed always perpendicular to the surface. So here we notice that the stool has a nice flat surface, so the normal force is straight up. But literally what the normal force is, it's a force that arises to keep one object from going inside a second object. Right? You'll notice that the bowling ball is not inside the stool, it's just sitting on the surface. But this happens with anything. So let me give you a third scenario here to highlight our thinking. My third scenario, well, it's just like this. So we have something like a wall. And if I take this eraser here and I push it into the wall with my hand. Can I do that? Yeah. There it is. Does everyone see this happening? So I'm pushing this eraser into the wall with my hand. Is the eraser moving? No. So again, the net force should be zero. We have no motion. So if we draw a free body diagram for this situation, well, I have a dot that represents my eraser. Does gravity still apply here? Yes. So gravity will still pull my eraser down, force of gravity. But in this case, I'm pushing it into the wall, right? So I don't know how hard I'm pushing, but maybe this hard. So let's say that's the force of push. So first of all, did the eraser move down while I was holding it on the wall? No, that means there must be a force pushing back. Or sorry, pushing up, because it did not move down, right? And it did not go into the wall, so there must be a force pushing out. So my question is, okay, well, if I'm pushing it into the wall, what force is keeping it from going inside the wall? Well, what do we call it? We could call it the wall force, or more specifically what? The normal, because it's what keeps the one object from going inside of another one. So this is the normal force. So it should be noted that the normal is still perpendicular to the wall, right? Is it opposite gravity? No. Is it the same size as gravity? Probably not. I mean, maybe coincidentally it is, but really how big the normal force is really just depends on how hard I push. I can push very lightly, I can push very hard. It's going to be the opposite of whatever I push it with. Because again, it's those electrons not wanting other electrons near them.
So is normal kind of like homeostasis, where it tries to bounce into equilibrium?
Basically. Now, can you break through that? Sure. You can break the wall. But we're going to try not to break walls right now. Maybe later. But then, if this is the normal, this is the force I'm pushing with, this is the force of gravity, what force is holding it up? Why doesn't it fall? Because what's interesting is I'm not holding it up. I'm just pushing it into the wall. So why doesn't it fall? Well, we already talked about a force that opposes motion. Friction. But basically, in order for this thing to stay up here, I just have to push hard enough to make sure friction can hold it. Because it turns out friction is actually related to the normal force, which we're not going to get into too much detail on that right now. So I want you guys to see a couple of things here. The normal force, a lot of times, is equal to gravity. Not all the time. That's number one thing. Number two, normal is always perpendicular to its surface, regardless if the surface is flat horizontally, flat vertically, or at some angle in between that. It's always perpendicular to the surface. The word normal in math means perpendicular. Okay? But it's the force that keeps one object from going inside of another one. But again, gravity is always down, right? So that's easy. Friction opposes motion, so we can see all of these different things in these couple of free body diagrams we have here. One last thing I want to talk about before we dive back to the notes proper is that normal force is actually the force that you see when you stand on a scale. Like if you've ever weighed yourself, like a normal bathroom scale, that doesn't actually read your weight, because your weight would be the force of gravity. It actually reads the normal force, which is why it could be wrong. You ever stood on a scale and it give you the wrong number? Y'all don't have no adventures. If you stand on a scale, matter of fact, if you buy a new scale, one of the things it'll tell you is make sure you put it on a flat, level surface, because it's actually going to display the normal force, how hard it's pushing on you. And if that surface is not flat, if it's slanted at some angle, well, it would actually only read a portion of gravity, not all of gravity. And so it's very important that when you stand on a scale, if you wish to see your accurate weight, that there'd be nothing else underneath the scale, like no carpet, no wires or anything, just flat floor. If you have it in one of these other situations, well, it's going to read something not terribly accurate. And this makes sense because, if you stand on a scale and like you hold your dog, well, is it going to read your weight? Well, no, it's going to read how hard it has to hold you and the dog up. So that's obviously not your weight in that case. Does that make sense? Because the whole deal is does your weight change based on what surface you're standing on? No. But scales are just an approximation. Like I said, if it's nice and flat, then we get like our first situation there, which we have with the bullet. Okay. So hopefully that was a little bit more detail on the normal force, because I don't want you guys thinking that this thing's some magical thing that just knows how hard to push. It's just electrons not wanting to be near other electrons. This slide and the next slide are really trying to emphasize the fact about mass versus weight. Mass is the matter that physically makes you, you. Right? That's why everybody's different. But weight is the response of that mass to the pull of gravity. We know the acceleration of gravity is 10. So if you knew your mass, you simply multiply by 10 meters per second squared, and you'll get your weight in newtons. Note that we're using the metric system, not the English system of measure. There's many reasons why the English system is inferior, mainly because they use pounds for force and pounds for mass. In some places, they even use pounds for money, because they really like pounds for some reason. But again, remember, the force of gravity is not the acceleration of gravity. So here, this talks about if you know the mass of the object, you can easily find the force of gravity on it. So here, this goes a little bit further, because if you know your mass, that doesn't change, right? Your mass is your mass is your mass. It's pretty constant, and it's very difficult to change. Some of you guys talk about, well, I need to gain weight, or I need to lose weight. Really, you need to gain or lose mass, okay? Which is why it's so difficult. But again, if you know your mass and you happen to travel to some other place, like a different planet, well, your mass is going to be the same, assuming you don't lose an arm or something. So if you look at this here, it lists the Earth, the Moon, Jupiter, and the Sun. And all of these places, notice that the mass is the same. For this particular person, it says 63.5 kilograms. So no matter where you go, your mass is your mass. And if you guys want to find your mass, well, you can stand on a scale. Or here, if you happen to know what it is in pounds, well, it says 1 kilogram equals 2.2 pounds. So if you take your mass, take your weight in pounds, divide by 2.2, well, then you'll have your mass in kilograms. So for example, I have a mass of about 220 pounds. So my mass in kilograms is only 100 kilograms. I say only 100, but I'm pretty much bigger than all y'all. So if you go to calculate your mass in kilograms and you get something bigger than 200, well, then just look at me, and if you go, oh, okay, I'm bigger than Mr. Dupree, well, that's probably right. If you don't think that you're bigger than me, and you get a mass bigger than 100 kilograms, well, you probably did it wrong. Okay. So here it talks about, well, once you know your mass, well, you simply multiply by the acceleration of gravity on that planetary body, you can find your weight. So for instance, here on Earth, this person weighs 63.5 kilograms. That would be about 623 newtons. It's obviously using 9.8 there. That's only about 140 pounds. So for instance, my weight, I have 100 kilograms of mass. Well, what's 100 times 10? That. So my weight here on Earth is about 1,000 newtons, which is far more than most people would want it to be. But if you go to the moon, your mass is still the same. So like I would still have the same mass on the moon. But to find my weight, I wouldn't multiply by 10, because that's not the acceleration of gravity on the moon. The acceleration of gravity on the moon, it being about 1/6 the size of the Earth, well, it's about 1/6 there when it is here. So you only multiply by about 1.61 instead of 10. And so you'll notice that this person weighs 623 on Earth, but they weigh 103 on the moon. That's significantly less. Like I said, it's about 1/6 of their weight on Earth. But notice their mass is exactly the same. Do you guys agree that the moon is smaller than the Earth? It is. Now, the next thing it gives us is Jupiter. Is Jupiter bigger or smaller than the Earth? Bigger. As a result, there's more gravitational pull on Jupiter. So if you could theoretically stand on Jupiter, the surface of Jupiter, its gravity is a bit bigger than 10. It's actually about, I think, 24.7 or 23.7. So it's like 24 or 25 meters per second squared. So if you take that same mass, that same 23, and you multiply by about 24, you'll get their weight on Jupiter, which is significantly more than what it was here on Earth. It's about 2.5 times as much. If you went from here to the moon, you would notice, especially if you watch the astronauts, when they walk on the moon, they almost seem to like jump or skip everywhere they're going, because they're using the same muscles that they would use here on Earth, except it's not as hard to move on the moon, so that just a little walk forward, they end up just like going a big leap, because they don't need to use that much force, but that's just what they're used to using. But if you take the same scenario, you go to Jupiter, well, most people probably couldn't move on Jupiter. I mean, when you think about it, if I put like 2 or 3 of you on top of you, most of you would have difficulty breathing, let alone moving. Now, probably wouldn't kill you, but you probably wouldn't be having a whole lot of fun. Now, the last scenario here is a silly one, but notice that the mass is the same even if we're on the sun, so there's a lot of problems with being on the sun. So let's assume that you've solved most of them, but you go there and you try to stand on the surface of the sun. Well, is the sun bigger or smaller than the Earth? It's bigger. Is it bigger or smaller than Jupiter? Bigger. If the acceleration of gravity is 10 on Earth and like 24 on Jupiter, on the surface of the sun, it's about 274 meters per second squared. As a result, you end up with a ridiculously high amount of force on you. And this force would be so much that it wouldn't, like Jupiter, like I said, you would have trouble moving or breathing. The sun, its gravity is just so high that it would just crush your body into a pile of goo. But that goo would have the exact same mass that it does here on Earth. Because your mass is constant, because it's literally the molecules that make you up. Like, just because you go to the moon or the sun doesn't mean you're something made out of different material. Does that make sense? So, that's what I'm trying to emphasize here. Your mass and your weight are different. Now, again, the reason why we're getting confused here on Earth is, I don't know about you guys, but I haven't really visited any other planetary bodies. So, but theoretically, humans are going to do that, right? Right? So here, this gives us a quick example. It says, why do we lay less on the moon than on Earth? Well, the moon has less mass, so it pulls on you less hard, essentially. Here, this talks about free body diagrams with good news. We already know how to make free body diagrams, so I'm just going to run over these rules real quick. So first, draw a model that identify your forces. Then we replace the object by a dot, and then we draw each force on that dot, and we label it. We have magnitude, and we label it with a label, like F sub G or whatever. That's basically it. So that's free body diagrams. So let's look at these examples here. We'll make a couple of more examples of free body diagrams. Now the first one says a book sitting on table. I'm not gonna go over that one because it's basically just like my bowling ball scenario we talked about earlier, right? But I do want to talk about these other three here. So instead of a book sitting on a table, let's look at a book sitting on a slight incline. Okay, so if we look at this one here, let me draw my scenario first. It might be a little hard to imagine if you've never seen it. But we have a book, ooh, terrible looking book. A book sitting on a slight incline. Now, is the book moving? No, it just says it's sitting there, so it's clearly not moving. So this is our situation. It's just sitting on the incline. So what forces are acting on this book? So I got my book. There's my book. We got gravity, right? Gravity is definitely down. That's usually a pretty easy one to start with. Are there any other forces happening on it? Normal. So now we have to be careful with the normal. Normal, by definition, is perpendicular to the surface. So that means the normal, like perpendicular to your surface, is going this direction, right? So my normal should be parallel to that. Oh, I'm going to try to put it on the top. That's a little bit better. So that's the force of normal. So again, is it exactly opposite gravity? No. All right, and that's important to note. It's not exactly opposite gravity, but this is kind of like the situation you would have if you put like your bathroom scale, like say you had like a rug in your bathroom, and half your scale was on the rug, the other half was just like on a tile floor. Well, it would be leaning like this, and it would definitely read a number, but this number is not going to be your weight. Does that make sense? It'll be something less than your weight, but maybe you want to lie to yourself, like, oh, look, I lost a bunch of weight. Are these the only forces? You weren't supposed to drop yet. Are these the only forces acting on our book? Friction. Now, you might be tempted to say, oh, yeah, that's the only force acting on it, or those are the only forces. But you should notice that this thing, in this case, would have a net force kind of going down the ramp, but is it moving? No. And so things that want to move that aren't being moved are usually held there by friction. And so we've got friction pushing back up the ramp. And so that's our free body diagram for the situation. Thank you for that. Oof. Everybody okay with that? So that's my book sitting on an incline. So now let's talk about a car driving down the road. So a car driving down the road, I'm not going to draw a picture of that. I think most of y'all can imagine that, right? Well, what forces are acting on this car driving down the road? Yeah, we could have a force of thrust. In order to determine a force of thrust, we're going to have to make up a direction that it's traveling. So, okay, sure, it's moving to the right. So, that's a force of thrust because it's driving that direction. Everybody okay with that? Is that all my forces?
And then you have the gravity.
Gravity. Gravity's down, right? Probably bigger than a force of thrust, but maybe not. Who knows? What else? Normal. In this case, what direction is normal? Up. It's probably a level road. So we'll make it about the same size. That's about right. Normal. Okay. Is that it? Yeah, there probably is friction. What direction is friction? Opposite way of thrust. Now,
It's not as big since the car's long.
okay, we can make it not as big. Okay. So, does this look correct now? Yes. Now, here's the secret. If we look carefully at this third scenario, it just says a car driving down the road. It doesn't really give us any details. It just says the car is driving down the road. So there's actually 3 different scenarios that this could be because it's not specific. What we've drawn here is definitely one of them. So is everybody okay with the one we've drawn? Now, specifically, the one we've drawn, we have the force of thrust bigger than friction. What that means is that our car is speeding up. It's not just going down the road, it's going down the road faster and faster and faster. Like it's going 30 to 40 to 50. You with me? That's one scenario. Another scenario would actually be that the force of thrust is the same size as friction. In that case, the car is still going to be going down the road, it's just not speeding up. It's going 30, then 30, then 30. It's just constant speed. Everybody okay with that one? The last scenario is actually going down the road, but your force of thrust is going to be smaller than friction. It might even be gone. That would be the case of the car slowing down to stop, right? It's moving along, it's going 30, then 20, then 10. it's definitely gonna be less than friction, it might not be there at all. Does that make sense? And with this scenario that it's given us, we don't know which one it is, it just says a car going down the road. So this is a pretty common one to assume, which is fine, but I want to point out that if it said a car moving with constant velocity, well then these two have to be the same size. If it said the car is speeding up, then it's definitely this situation. If it says the car is slowing down, well then thrust would have to be smaller. Everybody okay with that? All right, now the last one we have is a bowling ball falling through the air. We had some of that, let's just do it again in case y'all missed it. If I need to do it again.
All right, let's break the book. Let's have people.
So, now, let's do that situation here. So we have a bowling ball falling through the air. So I'm not going to draw that because it would just be a circle. But hopefully you saw it being demonstrated.
Does that need gravity without one of the, or not?
So we got gravity, right? And in the case of a bowling ball falling, that's it. I mean, you could theoretically have some friction with the air, call it drag or air resistance. But at the speeds this ball is traveling, that's not really a concern. So pretty much things falling, that's it. And if you had it falling through the air, you might have a tiny little arrow up here for some air resistance. Now, if we drop it, say, out of a plane, give it a good distance to fall, eventually this friction or this air resistance could get bigger and bigger and bigger to the point where it's actually the same size as the force of gravity. That's actually called terminal velocity. And that happens, like when you skydive. The friction from the air is actually equal to gravity. Does that mean that people just stop? No, they keep falling, they're just not getting any faster. Right? So that's it for this slide. So now we have Newton's first and second laws, and we've kind of talked about these already, so this actually takes not very much time. So again, first law, sometimes called the law of inertia. And remember, inertia is the tendency for an object to keep doing what it's doing. So the actual first law, remember, is written as an object in motion stays in motion, an object at rest stays at rest, unless acted upon by an outside force. Right? But again, the more mass an object has, the more inertia it has, the more likely it is to keep doing what it's doing. And so here, this gives us different scenarios, like a semi-truck versus a smart car and stuff like that. Obviously, the object with more inertia is, going to be the object that's going to be harder to move. So here, this actually gives us a couple of videos. I'm not going to play any of them in class. I might later at the end of class, but y'all can click on these links and watch the videos yourself. So inertia beads are actually just a bunch of beads on a string where it turns out if you pull the string, the object's in motion will actually stay in motion. It's a pretty neat video here. Then we have two about the tablecloths, which I did the tablecloth trick on Friday. And then these last two are kind of, objects that are in motion. And when we apply an external force, in the case of the truck versus the barrier, they run a truck into a barrier designed to stop trucks. And so you'll notice that it stops abruptly. And then the last one is a train running into a car that was stuck on the tracks. First of all, there's nobody in the train or the car. It's a safety down. And so you'll notice that the train hits the car, it doesn't stop for a while. Then that brings us to Newton's second law. Newton's second law states that when you apply a force to an object, it will accelerate, but how much it accelerates depends on, the mass of the object. So with the second law, this is where we're going to get most of our calculations from. So remember that with the second law, we said the force is directly related to the acceleration, but it's inversely related to the mass. So for example, if you have an object that you push with a certain force, if you double the amount of force you push it with, well then that doubles the acceleration. It's a direct relationship. If you push the object and then double its mass and push it again, Well, doubling the mass will give you half of the acceleration because it's inversely related. So directly related means that one goes up by a certain amount, the other one goes up by the same amount. Inverse means as one goes up, the other one goes down, but by the same amount. So here, this is basically just stating it all again. Acceleration is directly proportional to net force, inversely proportional to the mass. So again, if you're putting a 300-pound person on a swing versus pushing a 30-pound person, it's going to be easier to push the 30-pound person, right? Because they have less mass, so therefore they will get more acceleration. Here, this gives us a quick example about calculating this astronaut's weight. So it actually gives us two questions. It says, what force does the 75-kilogram astronaut experience during this launch of this magnitude, and how much more is this than their weight? Well, we can actually look at their weight first, because the acceleration of gravity is only about 10 meters per second squared. And it says for this particular launch, not that one pictured, there's actually no people on that rocket, but this is about 3.5 times what you experience just sitting here on Earth. So how much force do they experience? Well, if we take 75 times 10, them just sitting here on Earth, so force of gravity normally is just 75 kilograms times 10. So that gives us a force of gravity of about 750 newtons for this particular astronaut. Which again, this person would still be smaller than me. Which might sound weird, but actually when we had to launch astronauts using the Soyuz rocket, taller astronauts were actually too tall. Basically, if you were over 6'4", you were too big to fit on the Soyuz rocket. I'm not 6'4", though. But just as a kind of side note there, that astronauts can actually be hammered if they're too tall or too small. So if we want to figure out this particular force here, we just do force as mass, which is still 75 kilograms, times the acceleration, in this case 35 meters per second squared. And let's see here, we get a force of like 2,600, if I remember correctly. I don't know. 25 times 35. 2625. So again, this would be about 3.5 times this amount, which would be equivalent to having 3.5 of you sitting on top of you, or 2.5 of you sitting on top of you. Again, it would be very uncomfortable, and you probably couldn't do much. So yeah. Well, that's it for the notes. That's all we're going to cover right now. We'll cover the other half next time.